here. So what we're watching here is watching the ball move in the air. What happens is swing bowling usually does its best work 20 or 30 overs into the match, because you usually replace the ball every 40 overs into the match, because otherwise the ball gets a little bit too banged up and it gets a little bit hard, a little bit mushy and hard to hit and hard to bowl with. So the ball's actually going to swing towards the rough side, because what the fielders will usually do is they'll keep one side really rough, and they'll do that over the course of the match. They'll pick at it and they'll scratch it and dig at it. You're not meant to do it, but usually that's what's going to happen, and they'll make sure that one side stays perfectly smooth and as new as possible. So that's going to promote the turbulent flows on the rough side of the ball and the laminar flows on the smooth side of the ball. So that's why the ball is usually going to move towards the rougher side. But this always isn't the case, because sometimes if the ball gets so old, you can have something happen called reverse swing, and that's not really what we're talking about here. But what happens there is the ball deteriorates to such an extent that the rough side will get so deteriorated that it will start to take the characteristics of the smoother side. And so what you'll see then is the ball will actually swing towards the smoother side instead of the rougher side. And usually if this happens, the fielding team will usually just continue to go with it, because it's much harder to pick up for the batsman. But at the moment we're just going to talk about conventional swing bowling, and for that I'll hand it over to Corey for our hypothesis and analysis.
Okay, so going back to our slideshow here, if I can just start here on the hypothesis. Our main hypotheses are that the rotation of a cricket ball is due to a drag coefficient difference between the sides, creating an overall moment of rotation on the ball, and in turn this causes turbulent and laminar flows on each side that contributes to the drag coefficient difference. So if we go into our analysis now, we can talk about the drag equation, which we have pictured here: D equals CD times rho v squared over 2 times A. And this equation, essentially, the most important constituent in this equation is the CD constituent, which is the drag coefficient. This is usually determined experimentally, and it is what would determine the difference in drag force between sides, because all of the other terms in the equation would be constant across the two sides: velocity, area, density of air in this case. And so that's the main thing that we want to talk about with the drag equation, is that the difference in drag coefficients is the main factor that contributes to the difference in drag. And we can also look at the mass moment of inertia of a sphere, since there is going to be a difference in forces on each side of the sphere. We're going to see that a net rotation on the ball, and then whenever it strikes the ground and then takes off towards the batter, that is when you're really going to see a true change in direction, because it rotated in the air, and then when it hits the ground it grips and takes off in the direction that it is rotated towards. So this rotation is a pretty important part of the swing on the ball. And finally, we can look at our figure on the right side to apply the concept of turbulent versus laminar flows on opposite sides of the ball, which we talked about. And this figure is a pretty good illustration of exactly how the difference in flows causes the ball to swing. And in addition to the one side of the ball being rougher than the other, we can also talk about where it's shown in the figure, the seam of the ball. Once it starts to rotate, that can actually cause a disturbance as well and contribute to the difference in laminar and turbulent flow. So we can also focus on that, because that's just another factor that'll add to our swing. And that's pretty much our whole hypothesis and analysis.
The curve of the ball is due to the difference in roughness of the two sides. The curve is caused by the difference in drag coefficients and the drag force. If we want to analyze the roughness of the ball in terms of Reynolds number, we can think of it in terms of the Reynolds number of the rough side is greater than 4,000, which is a turbulent flow, and then the Reynolds number of the smooth side is less than 2,000, which is a laminar flow. And that is all.